Okay, welcome to this chat session. I look forward to interacting with you on specific questions. And until further questions come, let me try and say something on the two responses to the chat session earlier by two of you. One question is on atomicity. Okay, Abhilash, Vicky, hi. Yeah, please, go ahead. Maitreyan Velliyangiri. Yes, I'm able to see your typing. Yeah, start the questions. Yes. Okay. So, Amit Kumar. Oh, you were asking me how am I? Okay, I'm good. I'm quite well. So please, thank you for the question. But until you type the question, let me answer the first one, which was already asked. The question was on atomicity. I believe. What's happening? So what is atomicity? I believe this is what the person asked. Atomicity, of course, an elementary definition of atomicity is the number of atoms in a molecule or even in an element. For example, the element oxygen has 2 atoms in the molecule. The molecule itself, if you take about methane, there are 5 atoms. And then sulfur, yes, 8. If you think about it, the solid state structure of sulfur has 8 sulfur in the solid system, and therefore the atomicity is 8. For atomicity in the level at which the question was asked, I believe, is referring to the number of atoms in a molecule. Okay. Now, let me go back to the chat session to see if there are any questions from you. Yeah. Okay, so now, since there are questions, no, I don't see any questions till now. There are people who are listening to me. The second question that was asked to me is slightly more advanced, and the question is about coarse graining. This is question 1. Question 2 was about coarse graining. Okay, first of all, I'm not the right person to talk much about coarse graining because it's a sort of an averaging technique or technique in which the details of the dynamics or the details of the mechanics are not really necessary. So coarse graining refers to multiple ways of approximating detailed dynamics in the form of, in the sense of molecular dynamics. And I would say, as a general response, there is no single coarse graining technique that is universally applicable to my knowledge. I think they are all system dependent. And you have to define your system very clearly and the level of approximation that is appropriate for that system, not from the point of view of theory, but from the point of view of results that can be verified by experiments. So the coarse graining is applied only to that level. For example, if your experimental measurements are very, very accurate, then avoid coarse graining. Do the detailed mechanics or dynamics or whatever is the equations of motion or the system equations that govern the system, solve them. But if the measurements are averages, then coarse graining is important. From 2 examples that I know of, I can tell you, in chemical kinetics, for example, we often measure thermal rate constants. We find it extremely difficult, and also we require very, very specialized experimental setup, very costly setups to measure state-to-state, what are called reaction cross-sections. But thermal averaging and thermal rate constants through what is called the averaging technique is an example of what is called the coarse graining in that particular field. So if there is a specific model that you are looking for, please send me your question to my email and I would respond to you. In this forum, I would also look for lots of students who are asking questions directly related to the topic that I have been giving. It doesn't mean that you should not ask, but send it to my email. Okay, I'll be able to definitely respond to you. Okay, there is a question here from Amit Kumar on what is the difference between equivalent weight and gram equivalent. Okay, equivalent weight, the definition. Okay, let me write that. Equivalent weight. It's the amount of substance that will react with, if it does, that reacts with 1.008 gram of hydrogen. That's 1 gram atom of hydrogen. Okay. Now, this hydrogen is a reference point. It can also be said in more recent ways, the amount of substance that will release 1 mole of electrons. Release or absorb, accept 1 mole of electron, namely 6.022 into 10 raised to 23 is the number. So in terms of the electron theory. In terms of other equivalents also, H plus ions, if you talk about the acid-base reactions, then the amount of a substance or a base that reacts with 1 mole of hydrochloric acid. That substance is called the equivalent, gram equivalent of that substance. And the mass of that substance is called the gram equivalent mass or the gram equivalent weight. So the difference between gram equivalent and equivalent weight is that equivalent weight refers to the mass of 1 gram equivalent, and 1 gram equivalent is defined by any of these definitions, namely the amount of substance that reacts with 1 gram of hydrogen, the amount of substance that releases or accepts 1 mole of electrons in an ionic reaction, or the amount of substance in an acid-base reaction, the amount of base that reacts with 1 mole of H plus. And in the case of oxidation reduction reaction, also a similar thing can be done. I hope that makes sense to you. Okay. There is one more question. Sir, what is the meaning of the phase of an orbital by Sharmista De? Okay, phase of an orbital, yes. So let me go to the second page. What is meant by the phase of an orbital? Okay. Orbital is generally given by a function or represented by a function. And if you are referring to, say, hydrogen atom, the function is a function of the 3 coordinates of the electron, or this is a Cartesian coordinates. The Cartesian coordinate is assuming that the coordinate is centered at the nucleus, and the electron, this is the proton, and the electron is somewhere here. Then its position in terms of the reference axis system, XYZ. This is an approximate model in the sense that the atom doesn't move. This is known as a Born-Oppenheimer approximation. But assuming that we have it, the Cartesian coordinate representation, or we have also the radial coordinate representation, or theta and phi. for the wave function. Okay. Now, this is a function. The phase of an orbital is a complex number which is multiplying the function psi or theta phi. If you recall, this phase is not important because all quantities that we use in quantum mechanics are essentially related to the product of psi star and psi. If it is a probability, it's a direct product. It's a probability density. If it is an expectation value, then it's an operator in between the two wave functions, but it involves psi star and psi. And therefore, if you write the wave function with e to the I delta and something else, psi or theta phi, then whatever you put in here, either the operator or even unity for probabilities, this will be e to the minus I delta, this will be psi star, and this will be e to the I delta psi or theta phi. Therefore, the phase of the orbital is the sign in front of it in your standard text representation. But in principle, it is a complex number because if you want to have a -1, -1 is e to the I pi, a specific value, that is delta is equal to pi. That value is the minus sign. The sign of an orbital is important only when you combine two wave functions linearly. For example, if psi1 is given by something like let me say it the other way around. If we combine two wave functions, psi1 and psi2, please remember psi1 plus psi2 and psi1 minus psi2 will mean different things. Therefore, the phases of the individual orbitals or individual wave functions are important for such things. If we do psi1 plus psi2 star, psi1 psi2, psi1 plus psi2 d tau, here also the phase of the orbital is important. The phase is important only when it is part of a much larger system of wave functions. But the phase of an orbital or a single wave function by itself is not very relevant in either the normalization or in calculating the expectation value using that function only and only. If you use that function in a linear combination, phases are extremely important. Okay. So that was one question. And how do we define an orbital is a question by Velliyangiri, Maitreyan. Okay. Since you are referring to an orbital, I believe you are referring to an atom. How to define an orbital? I think that's what the question was. Let me just check. What is the... Yeah, how to define an orbital is the question. Okay. It's a wave function which is a solution of the Schrodinger equation. Which is a solution to the Schrodinger equation. Therefore, an atomic orbital is a solution of the wave function to the atomic Schrodinger equation. Atomic Schrodinger equation essentially means that the atom, which has a nucleus and many electrons, will have the kinetic energy for the nuclei, the nucleus, the kinetic energy for the electrons, and then the electrons will also interact with each other. The electrons will also interact with the nucleus. If you put all these things together, you will be able to write the total energy of the atom. 2 weeks from now, I will give you a complete picture of what is meant by an atomic Hamiltonian and what is meant by a molecular Hamiltonian. Therefore, if you are referring to what an orbital is and you want to know what should be defined. How do we define an orbital? The question is, the answer to that question is, it is a solution to the Schrodinger equation. Now, the solution may not be obtained through exact methods. The solution may be obtained through computational methods or approximate methods, and even approximate theories. There are many theories, approximate methods in quantum mechanics. Two most important ones are called the perturbation theory, and the other one is the variational theory method. These are methods to obtain solutions to the equation H psi is equal to E psi. So psi is an orbital if H refers to the Hamiltonian of the atom, or if H refers to the Hamiltonian of the molecule. It's a solution, exact or approximate. Okay. What are the, yes, there is a question by Abhishek, which says, let me see, I hope I have not. Okay, there's one question before by Himanshu. He's asking me, Himanshu is, what is my email? Okay, I have this all the time in all my lectures, but will also give you now. My emails are Mangal at iitm.ac.in. This is the IIT Madras email. And the other, my personal email, is mangalasundark@gmail.com. You can write to either of the email addresses. Okay. Next question I see on the chat session is, yes, what are the external factors that can deteriorate or deform the atomic structure? Good question. External factors that deteriorate or deform the atomic structure. Simple answer, possibly everything. But let me be a little more specific. For example, if you want to deform an atom, it's possible that you put the atom in a very high electric field or a very high magnetic field. The magnetic field is not as strongly deforming the nucleus or the electronic structure as the electric field will do. The effect of the electric field in the energy levels and the transition frequencies of the atom is known as the Stark effect. And the effect of the magnetic field, electric and magnetic field. Gravitational field is almost absolutely nowhere of any importance in the structure and the study of the atoms. But strong electric fields and strong magnetic fields are good sources for changing the structure of the atom or the electronic structure in some way or the other. The other very strong influences, of course, related to this. This can be static electric field, or this can be time-dependent or oscillating electric fields. The whole of spectroscopy is through the influence of the oscillating electric field and the magnetic field. Electric and magnetic field. That's the interaction is with what is known as the spectroscopy. Okay. So those are other examples. Now, since you are asking for the atom, I wouldn't say pressurizing, reducing the volume, and all these things are probably not so much. But if you are referring to bulk matter, yes, the entire structure can be deformed very quickly if you squeeze, if you apply very high pressure, or if you excite the atom and molecule to the other most obvious thing, temperatures. thermal effects. Temperatures, thermal effects. You can send the atoms through a shock tube, very high shock wave pulses can create changes in the structure of the nucleus. I mean, chemical reactions can be induced through the shock tube. So there are many phenomena. Today, lasers and shock tubes are very important, and shock tube experiments is tube experiments are fundamental for creating differences in the molecular energy levels and states, and even for creating what are called the deformation or deterioration. The last thing I would say is, of course, molecules undergo collisions, and temperatures are very important for increasing the number and the intensity of the collisions. High temperatures mean very high number of collisions and collisions with very high energies. Therefore, these are all some of the external factors which would influence the entire molecular structure and the atomic structure. Okay. I hope. If you want to know more, yeah, please continue to type questions and I will continue on that. Okay. Then there is the next question is, sir, how poisonous, it's also say Abhishek only, how poisonous nature of substance depends on chemical bonding or atomic structure or moving across the periodic table of elements. Good question. I don't think I know the answer directly, but I only know that certain bonds, particularly involving the hydrogen, involving the nitrogen, and involving sulfur and phosphorus, specific types, are biologically important for us. See, poisonous nature refers to the biological interactions of the molecules with the system. For example, it can be a metal ion that can be poison. If you think about the iron, you see anything that chokes the supply of oxygen to iron in the blood, the porphyrin structure and the hemoglobin, any substance that does that is essentially a poisonous substance. So there is no single criterion to say that this substance will be poisonous to every system, barring cyanides. And for example, I think they are probably universally poisonous all over. The reason why cyanides are poisonous to all of humans is that the cyanides remove the oxygen through a very strong complexation, remove the iron through very strong complexation, and therefore the oxygen supply, the oxygen carrier is completely destroyed. I mean, these are a few chemical bonds. That is, to my knowledge, there is no way of categorizing poison through the nature of a bond. The strongest bond that can be formed and which destroys the labile nature of the interaction oxygen carrier in the body, that's one example. The other can be the I don't think I know enough about it. So this is one example in which I would say close. And if you need to know more about it, send me the same question, and I will also try to pull up a good chemistry book which refers to chemical poisons and see if I understand there is any generality. As of now, no, I don't know the answer beyond that point. Okay. There's one more question by Amit Kumar. Sir, how to draw the graph in one-dimensional box with sine and psi square? Two different graphs that you mentioned in PDF. Okay. It's a very straightforward text question. So let me go back to that. Sine. Sure, yeah. Yeah, sine x 1D box. Okay, if you remember, the psi of x is root 2 by L, sine, let me write this as psi n of x, n pi x by L. The square of the function psi n square of x is 2 by L sine square n pi x by L. Okay. So one way to draw this graph, suppose the box length is 0 to L. The wave function is only a function of the position at any point. This is x. So you are plotting psi of x as a function of x. Since the first one, let me take psi 1 of x. That would be root 2 by L sine, since n is 1, this is pi x by L. Pi x by L sine. This is very easy to see from 0 to L, because at x is equal to 0, this is 0, and x is equal to L, this is also 0. And it's a sine graph. So you must know that the sine graph is essentially something like this. It's an oscillatory wave function. Okay? It's a half wave. What is the square of the sine graph? Psi 1 square x. Sorry, it's not root 2, it's 2 by L sine square pi x by L. Okay? So this height for the sine wave function is the maximum amplitude. So this is root 2 by L, root 2 by root L. Okay? If you have to plot this using sine square, let me use a different color. Okay? So now I want to plot psi 1 square 2 by L. Let us assume that root 2 by L is less than 1 in some scale. Let's assume that. Then 2 by L is definitely also less than 1, but it is what is this? If this is say 0.9, square root is 0.9, 2 by L is of course greater than that. Okay, so you are 2 by L will be somewhere, probably this is something you can write. Okay, but the wave function is a square, sine square. Therefore, and you see that near 0 and near L, the sine functions are very small values. Therefore, the sine square has even smaller values. Therefore, you would have something like this. The maximum will still be at pi by 2. You will have something like that. This is a sine square function, psi 1 square x. Now, if you repeat this process for all values, different values of L, for example, psi 2 of x will be, it's a full wave now, because psi 2 of x from sine 2 pi x by L into root 2 by L. Therefore, it goes to 0 at x is equal to L by 2. That's a half point. This is the L by 2. And therefore, what you have is, let me draw the line somewhere from here. We'll start drawing the graph here. So if this is root 2 by L, this is the height. If you think about it, then the wave function goes to 0 at L by 2, and then it goes back again to 0 from the bottom. But what about the psi 2 square? Psi 2 square is all positive. Therefore, even the square of this negative function will be positive. So what you see for a psi 2 square is essentially something like that. And the negative side also becomes positive, and this is exactly that. Okay? This is psi 2 square. Now you got the picture. Therefore, you see psi 3 will be 1.5 times. This is 1. The first one is half. Therefore, this is the next one will have 3 parts like this, and therefore 3 parts like this, and so on. I hope you understand. Yeah, you are thanking me for my valuable time. I think the valuable time of a teacher is valuable only if the students learn. and the students are interested in learning. Otherwise, the teacher may do whatever he wants to do or she wants to do. Therefore, my time is as valuable as you are willing to learn. Thank you. Okay, there's one more question by Parida Gupta. I'm sorry, I missed that. What is the difference between an orbital and a subshell? Let me go here. Difference between an orbital and a subshell. Okay, let me clarify the term because I do not understand the difference between the two, but let me understand what you mean by an orbital. Orbital is the full wave function. Okay, if you are referring to, say, hydrogen atom, by a subshell, you probably had something in mind. What is 2p x? What is 2p y? What is 2p z? If you think about 2p as a subshell for the principal quantum number 2, if that's what you mean, then I must tell you that every subshell, the way it is written, is indeed an orbital. Okay? 2px tells you very clearly that the principal quantum number n is 2, the angular momentum or the azimuthal quantum number L is 1, and the m is not defined because it's x or y, but m is defined for 2pz. If you want to write 2pz, m is equal to 0. So you have a very clear prescription of all the three quantum numbers. Therefore, the wave function that has all these three quantum numbers, psi or theta phi, is written as 2, 1, 0. If you want to have a quick look at Macquarie, so one of the most well-written, excellent books in quantum chemistry, you can see that the specification of all the three quantum numbers, even if it is a subshell, precisely means that it is a full orbital. If you say a p subshell, and don't say whether it is 2p or 3p or 4p, then all you are referring to is to the angular part of the wave function. Okay? Remember the difference between this angular part, this part, and this part. The difference is that in the first one, you have the specification of the radial as well as the angular part, because the radial quantum number 2 and the L equal to 1 specify a radial function, and the 1 and 0 specify an angular function. Remember the wave function for the hydrogen atom. I will teach that in the next week's lessons. Psi n L m or theta phi, if you look at it, is written essentially as r n L of r, y n y L m of theta phi. As long as you specify the three quantum numbers together, it is always an orbital. But if you simply want to say 2p shell, 3p shell, 3d shell, 4d shell, there are 5d orbitals for 3d, but there are always 5d orbitals, whether you are in the principal quantum number 3 or you are in the principal quantum number 4 or you are in 5 and so on. Therefore, if you refer to d subshell and do not say whether it is 3d or 4d or 5d, then that's what you call as a subshell. But the moment you say it is 3d, you have specified an orbital 3D, then there are 5 labels, namely x square minus y square for the one of the orbitals, xy is the other orbital, xz, yz, and then you have 3D z square, which is 3z square minus r square. So the specification of these essentially means that you are referring to an orbital. The specification of a D shell means that you are only looking at the angular part of the wave function, and therefore that you may call as a subshell. But no, I would always refer to an orbital with a full set of quantum numbers to say where the electron is or what type of wave function we are referring to. Okay. Then there's a question by Sharmistade. What is rest mass? Can we not simply use mass? Okay, good. What is rest mass? When the speed of the object is not anywhere close to the speed of light, the mass of the substance, if you remember, is given using this relativistic formula 1 minus v square by c square, where c is the speed of light in vacuum. And m0 is called the rest mass. So when v is much, much less than c, or when v by c is much, much less than 1, you see m is approximately equal to m0. Therefore, the mass of the substance is known as the rest mass, is equal to the rest mass of the substance. It's an approximation. Okay. Any speed, the moment the particle has a speed, the mass of the substance in its motion is different from the mass of the substance when it is at rest by this formula. Okay, this formula. Therefore, if you say m is approximately equal to m0, it's because the velocity of the speed of the particle is far too small compared to the speed of light. Now this fails in the case of photon, because photon travels with the velocity of light. Photon is light. Is a component. I mean, this is the theory of Einstein that light consists of photons, quantas. Therefore, what's the rest mass of the photon? 0. But it travels with the speed of light. It has a momentum. And the momentum for the particle, the light, is given by, P is given by h by lambda, namely the wavelength. Momentum is something that we understand is due to some mass traveling with a certain velocity, not with respect to electromagnetic radiation. The momentum of the electromagnetic radiation is clearly, this is the de Broglie formula. So an object which doesn't have a rest mass can have a momentum. An object which has a rest mass at 0 velocity will have a mass which is slightly different from the rest mass. It will always be this one. The mass is, because this factor, you remember, if v by c is anything less than 1, this is less than, the whole square root is less than 1. Therefore, you see the mass is increasing. That is why, as the particle speed increases, the impact of the particles, the momentum that the particle carries changes with its speed, not simply by mv, but also the fact that m itself is changing. Okay? So this is the difference between a particle at rest and a particle in motion, and the two masses are very nearly the same if the motion is very slow compared to the speed of light. And in the case of light, there is no rest mass, but the speed of light with the wavelength of lambda being the wavelength still gives light a momentum, a particulate property. Okay? Okay. Yeah, keep looking at these lessons, and I will try and put more and more video tutorials for problem solving. The whole of quantum mechanics is more and more, you feel more and more comfortable with it. Please don't ever try and say that I've understood quantum mechanics, okay? Not very few of us in the world really understand quantum mechanics, but we all work with it. The quantum is a very beautiful theory which is practical for all the atomic scale phenomena. So keep solving more and more problems. And I'll also indicate towards the end of the course a whole list of problems and some of my lecture notes. Some of you have asked me for sharing the lecture notes. Yes, I will. And I have started putting in the first week's lectures. Now I have the second and third week's lecture notes. I will also put them up. Okay. We have some more time. So if there are any questions, let me know. Okay, there is a question here. Oh, Prashanjit is asking, my own TA is asking a question. How close today's quantum chemistry is to understand from theoretical perspective an organic chemistry reaction mechanism? Prashanjit, I think I will talk to you in the lab as well, but since you have come streaming, let me also answer you on the streaming mode. How close? It's as close as you want to compute, depending on the ability to compute, as well as the details of a reaction mechanism that you want to know. Okay, it's quite subjective. But today, reaction mechanisms can be followed in computational methods using very high-end computational techniques like this one, CCSD, that is coupled cluster methods, and probably even very, very high scale density functional theory methods, and so on. So I don't think that is a general answer, but it's quite close. Today, an organic reaction mechanism can be quite well elucidated, unless the reaction mechanism involves huge molecular species. If you are talking about small molecule systems, they can be very thoroughly studied using quantum chemistry. Okay. Okay, there is another question here by Shamali Grover. What is the graph for x square e to the minus x square? Okay, so let me draw that. Okay. Plot x square e to the minus x square. Actually, it's very easy. What you should do is to put down some values and then get some limits and connect the points between them. Okay. Now, x squared e to the minus x squared. First of all, f of x, if you write this, this is f of x as a function of x. One, f of x is even, meaning f of x is the same as f of minus x. Therefore, whatever you do on this side is going to be exactly the same on this side. Same as on the right side, mirror image. Mirror. Okay. Now, at f of x, for x is equal to 0, this is 0. Okay, fine. Then as x increases, e to the minus x squared decreases, but x squared increases. So you have that. It keeps on increasing. Okay, like a parabola, x squared. But the point is the parabola is slowly brought towards closer to the x as a function of e to the minus x squared. And then there is a point at which this whole thing becomes a maximum. X square effect is maximum. Beyond that, e to the minus x squared decreases so fast compared to x squared increases that you will have that. Okay? This, of course, goes to 0 only at x is equal to infinity. It doesn't reach. So the graph, I mean, this pointer is so thick that you can see that it's meeting here. But if I have to write it in a form that's visible, let me write this the following way, draw this in the following way. It reaches infinity only at 0. Okay? Since this side, sorry, it's this way. The inclination is wrong. Let me draw the inclination. The inclination should be this. Okay? And you have exactly the same thing on this side. Let us see. If I have to put this in as a mirror, something like that. These two are the same on either side of x. This is minus infinity. So this is x squared e to the minus x squared. There are two maxima and a minimum, but the other minima are at the infinities, plus and minus infinities, they are 0. That's the other minima, which we don't consider. Okay, Nishav Yadav. Sir, please share notes related to mathematical concepts in quantum chemistry or suggest good books for the same. Yes, I will do that. In my lecture also, I have mentioned several times, but let me tell you a little bit. The good books I have mentioned, let me do that in the next video. I will give you a list of the books. Okay. So, and you have Nairit Biswas has a question: how dx square minus y square and dz square orbital defined by its orientation in space? Here. Okay. So dx square minus y square orbital. Dx square minus y square orbital essentially is an orbital wave function. Suppose you write this as this is the x-axis and this is the y-axis, and let us get rid of this. Let's do the z-axis this way. To do that, then the dx square minus y square is a function that basically is pointing along the axis x and along the y-axis, x and y. Looks, but let me draw it a little bit more without the z-axis in the picture. Okay, let me draw this slightly. If you draw the x and y-axis as perpendicular in this plane, then it's very simple and it's easy to see that this is going to be dx square minus y square, and this is going to be dx square minus y square. Where is the z-axis? Z-axis is pointing perpendicular to this screen or your screen. And therefore, this orbital in 3 dimensions is actually having a lobe kind of thing around this, which is axially symmetric about this axis. Okay? Like this. So the lobe will be plus z and minus z axis towards that. This is dx square minus y square. Then the other orbital that you have asked is dz square orbital. Now for dz square orbital, we do need the 3-dimensional picture, but assuming that we have this as the z-axis and the xy plane is this. You do that, for example, if you do this and that, then the dz square orbital is something like that. Sorry, these both are equal in size. They are both equal in size. Very poor drawing, but it's okay. You will understand that these two are identical. And then you have a ring that goes tangential to the. Please, I shall discuss this in my next lecture, next week's lecture, week 5, isn't it? Week 5 lectures. Please wait until I load them. Week 5 lectures have all animations regarding all 2D and 3D animations. And you can see them, and I will also leave the animations. There are 15 into 2 flash files. all these animations will be available to you. So until then, I'm not able to give you a full 3D picture, but usually what one does is also to put the plus and minus signs in these orbitals. And here what you would do is, this is the plus and minus signs. And why these things come and how this looks in 3 dimensions is something, please wait until I give the lectures in week 5. Okay. Now, the other question is, thank you, sir. We study particle in 1D box. How can it be one-dimensional if it is a box? Yeah, actually, the box is a pretty bad word. Okay. The box is only to indicate, let me go back. What is a 1D box? I can understand that. A box cannot be 1D. Box has to be 2D. What it means is the following. What it means is that the coordinate available to the system is between 0 to L. The wave function can be described only as a function of x. But if the wave function is root 2 by L, sine pi x by L, for example, you need to plot it. But then the other thing that you need to know is the potential at this point. The potential at this point, V is infinity. V is infinity. The potential everywhere else is 0. Therefore, most people put a pictorial representation saying that this is the 1D box, this is the 1D box, and so on. All it means is that there is no point beyond this x is equal to 0. There is no point. The particle cannot be anywhere here. The particle cannot be anywhere here. No, it is not allowed. The particle is limited in its motion only to this region, namely x is equal to 0 to L. Okay? X is equal to 0 to L. So the coordinate that you have to worry about in this problem is the one-dimensional. The one-dimensional refers to the fact that x is from 0 to L. The rest of it is only pictorial. It's only to illustrate that the particle has potentials infinity. Therefore, here the psi is 0. And here the psi is 0. And in all these points, psi may be 0 only at few points. And these are called the nodes. Therefore, for each point, you associate a wave function psi x for each point. And since you want to plot that for each point, so usually you do this by either this or by this or by a 3-wave function, all those things. Those are all pictorial representations of a wave function as a one-dimensional function. So 1D refers to the fact that it is one coordinate and limited to a region from 0 to L. And it can be 0 to L, it can be minus L by 2 to L by 2. It can be minus L by 3 to plus 2L by 3. Essentially, what you are saying is a region of length L. Region of length L. The functions will be different for different cases, but the probabilities will not change. The squares of the wave functions will be such that the probabilities and any measurable quantities do not depend on where we consider the x value to be. As long as we say that L is the length of the region and everywhere else the particle is not to be found, the physics doesn't change. The geometrical representation of the whole thing may change a little bit here and there. Sir, where can we get your other lectures on atomic structure and quantum chemistry? Please wait until the IITM chemistry website is fully functional in a week or two, and we will try to add all the lecture notes by all the faculty members who have contributed to the NPTEL through links and subject-wise. Maybe in a month's time from there, we will add them so that you will continue to visit IIT Madras chemistry website as well as the NPTEL website to find out more lecture notes. But if you need anything specific, you always have the freedom as a student of this course and also as generally studying, right? Send me an email. I will definitely find time to respond. And if I have already lecture notes available, I'll be able to share with you. Okay? Please contact, yes, by email. Whatever is possible for this course, I will put it up in this course domain. Okay, there's one more question. I will definitely, Sharmista Day, I will definitely do my best to come in as many sessions as possible during the course. What is important for me and other teachers and other NPTEL coordinators is that you take science seriously and take the science forward in the best possible way. Okay, so yeah, we'll do our best. And Nisha has asked me a question, sir. We apply the model of particle in a box to conjugated system, but doesn't that involve more than one electron or particle? Yes, absolutely. That's a very, very good question. And I'll tell you what should be done in that model. Yeah. Let me share the screen for a minute. Okay. Yeah, so let me go to the next screen. Yes, you are right in saying that there are many electrons. But please remember, the model says clearly, ignore the interaction between the electrons. It's an approximation between the electrons. You know, a much more accurate model for studying the conjugated systems is the most beautiful theory known as the Huckel model. Okay. But that's much more advanced. We will not do that here. In this course, I will not do that. Or maybe towards the end of the lecture, the end of the course, I may say a little bit about in 1 week or 2 weeks, a Huckel lecture. But ignore the interactions between the electrons, which means you assume that you have a whole community of people or whole community of electrons in your system, which behave as though they're all independent of each other. Okay? And they are told clearly, no more than 2 people can go into any house. Okay? The house is the energy level. Okay? So which 2 will go into it? Well, electrons are indistinguishable. So there are questions which tell you that the most you can do is to put 2 electrons is basically to give you an idea that there is some principle called the Pauli's exclusion principle, which states that it's not possible for fermions, or particularly in this case electrons, 2 electrons cannot have the same quantum numbers. All the quantum numbers cannot be the same. So if you do that, in this case, there is only one quantum number, namely the n1, n2, etc. Therefore, only 2 electrons can be with their spin. The spin is not part of the whole discussion. The spin comes later. Therefore, if you ask, how can we do this, and why not we put these 2 electrons like this, all these questions don't have any meaning at this level of the lecture, because I've not even introduced you to it. So what is told to you is that ignore the electrons interaction, assume that only 2 electrons go into, so you can put probably 2 dots in that level, and put 2 more dots. Don't worry about the spin, and so on. So if you have a C6, a 6-fold, which means what? A CH2, double bond CH, single bond CH, double bond CH2, CH, CH, single bond CH, double bond CH2. 1, 2, 3, 4, 5, 6 carbons. Okay. And what about the electron? Will the electron stop right here, or will the electron stop right here? Approximation. It tells you, assume that the box length that you have is this length. The electron doesn't go into the CH2 region, or see, you have to put meaningful approximations to say, what is the ballpark figure in terms of the difference between the energies of the electrons from the electrons which are fully in all these 3 energy levels. So you will have 3 energy levels with these 6, how many? 1, 2, 3. Yeah, there are. So there are 6 electrons. Therefore, it's a 4th energy level, which is not occupied. So if there is energy given to the system, what will be this energy transition? So this is an approximation model. A much better model to study the one-dimensional electronic energy system is the Huckel model. And then, of course, you have the polymeric chain models. Much more rigorous theories are there. And finally, the whole thing can be even done computationally using the best known wave functions and the best known basis functions and so on. These are all different levels of approximation to different degrees of accuracy that you want to solve the problem for. And therefore, in the beginning, you solve the problems using simple methods. It doesn't mean that the method is right. The method gives you a window and an application scenario for you, and then you improve your calculations with better and better methods. Okay, my email ID is already there in the screen, so let me just go back to the screen earlier. Okay, I'll show you. Somewhere here I wrote down my email. It's one more question. It's also there in every lecture, because in the first 1 minute, I say every time that I'm a professor of chemistry in the Department of Chemistry. I'm sure by this time people would be bored listening to that. That's just a header to give anybody the origin of that lecture, if they are looking at the lecture in the middle of it. Suppose they didn't follow the whole course, but suddenly somebody finds in the YouTube, there's a particle in the box, and you find a lecture from me. Who is this? Therefore, every lecture has a header and a footer. This header says clearly my email ID. So please feel free to contact. Okay? Yeah, so it's about 11 o'clock. So I think the session was meant for an hour. And I thank all of you who were in the session and who I believe got some answers. And if you think that you were not clear, obviously use the discussion forum. And the others who have not been able to come in, please use the discussion forum. Once in a while, I'll join the discussion forum. I have three wonderful teaching assistants, all of whom are my PhD scholars. And therefore, they are able to basically answer most of the questions, and I only come in to add some additional inputs and so on. But I am following practically all the questions that all of you have been asking every now and then. Okay, so let's close the session now, and we will meet again next week. Next Sunday, I will be available, but let me find out if NPTEL is able to schedule another session next Sunday. If they do, you will receive a mail that will be another chat session on next Sunday. Until then, happy learning, happy reading. See you all.